Hey everyone. We are still talking about derivatives, so we're just going to there's a few more ideas I want to get in about them. So the first one is a pretty intuitive idea. So I'll remind us, right, we've got a couple notions of the derivative. If I'm given a function f, then f prime of x, right? So of course we have the limit as h goes to 0 of f of x plus h minus f of x all over h, right? That's like our algebraic definition. And then we've connected this to the slope of the tangent line, as well as the instantaneous rate of change. Right, so these three ideas are all connected. Derivative, we can think of it as, depending on context, we'll use all of these ideas. Right now, I want to focus on the second idea, the slope of the tangent line. So if the derivative tells us about the slope of a tangent line, that's information about the shape of the graph, right? So we can use derivatives to understand the shape of some function's graph, which is really a way of knowing about its behavior, right? If you've got a function describing the profits at your factory, you might want to know if the slope of this profit function is positive or negative, right? Are profits going up or profits going down, right? So the shape of the graph tells you information about what you might want to know about, right? The behavior of whatever little piece of the universe you're trying to model with your function. So let's look at this function here. This is a function f that's over there, but I'm not too concerned about what it is right now. We're not going to try to find the derivative. We'll be able to do stuff like this in a not too distant future. But for now, we just want to think about what the derivative means. So let's try to get a picture. If this is f of x, let's try to get a picture of f prime of x, right? So let's think about some things that we might know about it. For instance, if I imagine a tangent line right here, oops, and down at this spot below, right, they look to be more or less horizontal, right? The tangent line we imagine looks to be horizontal, which means it has a slope of 0. So if the function, the derivative function, f prime of x, at about the peak, right? I'm just eyeballing it. So maybe it looks like near 1 and near -1, the graph must be equal, or the function must be equal to 0, which means the graph would pass through the x-axis, right? Let's focus on this. Well, actually, let's look at the point where our function f goes through 0. This is the steepest part of the graph, and it looks to be going up in a positive direction. So this should be the highest value of the derivative, right? The steeper the function, the higher the slope of the tangent line. And so we could look at this line here and try to estimate. It's a little hard because my scales aren't uniform, but maybe 3/4. I'm just trying to estimate the slope of a line here, right? If I move from, so let's sketch it in. If I was to, let's use a different color, right? The tangent line at 0 would look something like this, right? So it's going from like -1/2 to +1/2, maybe not quite. So there's a difference of a little less than 1 in the run as we go from left to right, and up and down. We're eyeballing in there. I'm going to just guess this at somewhere, looks to be maybe a little less than 1, something like that. Just trying to eyeball what this might be. So I'm going to put in a value about here. Oops, I need a pen. There we go. All right. So all I really care about now is like a qualitative assessment. This is the highest point of the graph because the slope is the steepest here. So let's think about what happens to the function f between 0 and 1. It goes from being its steepest. It looks like it has a very similar steepness for a while, And then close to this peak, it starts to flatten out rather quickly. So our graph stays relatively at a relatively similar height for a while, but then drops dramatically to get to that 0, right? That's where the graph has a horizontal tangent. So the derivative should be 0. After this, let's imagine some tangent lines on this side. We have tangent lines that are negative, right? And so they go from 0, it gets to be, it's a little bit of a steep tangent line here, but then the tangent lines start to flatten out, right? When we get over here, this is a very flat tangent line, meaning nearly 0. So we must go past 0, we get negative tangents, and then we start to get closer and closer to 0 as our graph goes off to the right, okay? A very similar thing happens in the other direction. Let's start at -1 and think what happens between -1 and 0. We have a very flat graph, slopes near 0, and then slopes getting steeper and steeper towards this maximum point, this maximum steepness. So this is getting, it goes from very flat to steep very quickly. It should look very similar to the right half of the graph. Right, it goes up very quickly and then maintains this steepness, right? All the tangent lines I can imagine drawing near 0 are all very steep, okay? And we also get a similar shape in the other direction as we go to -infinity. Look at the slopes of the tangent lines here, as I'm imagining them, right? They're steeper over here, and they're all negative. And as we go towards -infinity, as we look at the graph to the left, they're getting flatter. So it looks like something like we saw on the other side. It's going negative, but then getting less negative. I know this drawing is pretty sloppy, but I just want to get the idea of connecting derivatives to the shape, right? So this is f prime of x, or a very rough sketch of it, right? Based on what we imagine, what our intuition tells us these tangent line slopes should be, we imagine f prime would look something like this. Let's look at the actual f prime. Okay, so our picture did not match up, but it's not bad, right? We didn't get quite high enough, but we got the zeros pretty close, and this behavior of going off to 0. Let's clear my drawings now. We see all that behavior we were describing happening, right? The steepest point is right at x equals 0. As we move to the right, the graph gets much, starts to lose its steepness until it peaks and has a 0 tangent line, slope of the tangent line, and then gradually gets closer to flatness from the negative side. And then a similar thing in the other direction. So this will take some work. You'll want to practice thinking about graphs and their derivatives and how the shapes are related to each other. Okay, let's move into actually, let's do one more example and call that it for this one. And then I'll save the other stuff for another video. So let's look at the second example. Here is, we're going to look at a graph of sine of x and imagine what its derivative will look like. Let's see, let's go from -2 to 2. Okay, there's our sine graph. Let's play a same sort of game. Let's think about some easy places where we can think about this graph. So for instance, wherever this graph peaks, the tangents are going to be horizontal, right? As it turns around, there's this perfectly horizontal tangent. Those are all places where the derivative should be 0, right? So I'm just going to mark in these zeros. Meanwhile, similar to the last graph we looked at, this looks to be about the steepest part on this graph. There's other parts that are probably the same steepness. They all seem to be steepest at these intersection points, right? Well, what is the steepness there? What's the slope of a tangent line there? I'm going to use something we noted earlier in this video series, that if we look at the limit as x goes to 0 of sine of x over x, this is equal to 1, this limit. We showed that in an earlier video. And we thought about this by thinking that near 0, sine x is approximately the same as x, right? If you put the line y equals x in here, let's just go ahead and do that. Whoops, turn that off. Right, we see that they line up very close right there. That has a slope of 1. That looks pretty close to what our tangent line should be. So I'm going to guesstimate based on that information that the slope here is a positive 1. So my graph should go through there. In a similar way, I'm going to guess that here, where we have a similar shape but now going down, we're going to go down to -1. Here, we're also at -1, and +1 would be back over there, but for this portion that we're looking at. So let's connect these pieces of the graph. Let me make this a little easier to look at. Let's get rid of these tangent lines. We want a graph that goes through these points. Let's turn off graph of sine. I want to make a graph that goes through these points. All right, let's put our original graph back up now. So notice a few things, right? So I more or less connected those points, but let's do a little more analysis of this. So for instance, at this point of -1, sorry, let's start at this 0 over here, where we imagined the horizontal tangent line. So we have a 0 slope. What happens? As we move to the right, the tangent lines get steeper and steeper. So our derivative, the blue line, which is f prime, should be getting more and more negative, and it keeps getting steeper and steeper until we get to this point here that looks like the steepest point that we estimated at -1, and then it remains negative, but it's getting less steep, especially right towards the end, and so we get back to a horizontal of 0. We start to increase, our tangent line slopes increase until we get to the steepest point at 1. Right, when x equals 0, it looks like we have a slope of about 1, so our derivative is equal to 1 there. And then as we move on, it's still a positive. These are positively sloped tangent lines, but getting less so. So our derivative is decreasing until we get to 0, and so on and so on. Okay. We haven't shown anything, but it's looking at this graph, we see that let's actually put in the real graph. Sorry, I'll clear what I have and put in the actual derivative. So very similar to what we drew. And we might make a guess that this derivative of sine is cosine. This looks very much like a cosine graph. This analysis hasn't proved that, but it's going to turn out to be good intuition. But what I focus on now is how the shape of the function and its derivative are connected, right? So here we have the red graph as a function, the blue graph as its derivative. And if we follow the values of the slopes of the tangent line, should coordinate with the values of the derivative function. Okay, that's it for this one. We'll do a couple more videos with a few other ideas on the topic of the derivative. All right, thanks everybody.